All right. This is a video. That's the best I got, people. This is a video for simple and physical pendulum. Hey, that's better than I thought. So we're going to talk about simple and physical pendula. Pendula, of course, being the plural of pendulum. So we'll see how that works out for us. We got that going. So, like I said, we're going to talk about those two things. I mean, I think you probably last year saw the equation for the period of a simple pendulum. T equals 2 pi L over G. Okay. But where it came from is kind of a weird thing. And it's something that I know didn't get explained a lot when I taught Physics Accelerated. So I definitely want to explain where that comes from. We know that for anything to exhibit simple harmonic motion, it has to follow the one specific rule. For any simple harmonic motion, the second derivative of the position vector with respect to time has to be minus omega squared, the original function. That's the rule. So, first thing we have to do is come up with a good expression for that. And then we can work from there on it. Okay, and we can figure it out. Okay. So, what that means for us is first we got to draw a little picture of this thing. So we have a pendulum. There's a bob. We know it has a length of L. And we know this has a mass of M. And if I let go of it here, it has a restoring force. It wants to go, it has a downward force. If I were actually drawing the force diagram, it would have tension and mg, which is exactly what you would expect. The difference is that it's moving in a circle. So the restoring force that moves it back is going to be the one that acts in the direction toward motion. If this is the angle that it comes from, this angle here, theta, then when we break this up, this would be the angle theta, which would mean that this component would be mg sine of theta, because it would be along that axis. So that means that the restoring force is going to be mg sine of theta, which is pretty close for small angles. For small angles, the sine of theta is pretty close to theta. I mean, try it for angles under 20 degrees, or what is that, pi over 6, pi over 5. You should be able to get that to work. Again, that is a name. They call it the small angle approximation. And actually, if you want to be technical, it's also about the same as tangent of theta, too. So, but in any case, the reason we do that is because that means we have that the force of x equals mg theta, which if you want to be technical, well, again, since they're about equal, that's going to be equal to, I guess it would be negative because it's restoring, my fault, and negative mg x over L. Sorry, x over L, where x is the actual amount moved in the horizontal direction, and that's the length. Well, that plays the same kind of role as, the restoring force for a spring, F equals minus kx, where this is actually going to be the same thing. K is going to be equal to G, or mg over L. So if we go back to what we learned about omega, the angular velocity, the angular frequency for a spring mass pendulum, which is K over M, then this will be mg over L all over M. Those divide out. You get G over L. And since the period equals 2 pi times the angular frequency, we can go ahead and divide it by the angular frequency. Then we can say that it's 2 pi, the opposite of this, L over G. And again, that just gets us back to the equation we talked about originally. The frequency is obviously going to be the inverse of that, 1 over 2 pi G over L. And again, this is for a small, small angle approximation. That's the key important part. So again, if you have a pendulum of 2 meters on the moon, where G is 1.63 meters per second squared, we can find the period pretty easily. It's just 2 pi 2 over 1.63, which according to my calculator, come on, calculator, there must be. There it is. I'm just an idiot. There we go. Come on. Okay, it's going to be 2 divided by 1.63. 1.22. Take the square root, which on this calculator is just inverse x squared. Oh, I just realized this isn't quite in your frame of view. Sorry. Okay. And then I took the square root, and I take that times 2 pi 6.28, and I get that the period is going to be 6.96 seconds. Cool. All right, and that's going to work. The second part of the video will have to do with changing the, will have to do with the physical pendulum, which is really similar.